In 1831, Michael Faraday in London and Joseph Henry in New York independently discovered electromagnetic induction. I am going to demonstrate electromagnetic induction with an experiment similar to the one that Michael Faraday performed. I have an ammeter here, and I have 3 coils. I have a coil with 1 loop, 10 loops, and 100 loops. I also have a bar magnet, and I will start by connecting the single loop coil to the ammeter. I now have the single loop coil connected to the ammeter, and I'm going to move the bar magnet into and out of the coil. And if you watch very closely, you can see a slight deflection of the ammeter needle. Okay, so now let me connect the 10 loop coil. And then I'm going to do the same thing. I'm going to move the bar magnet in and out of the coil. Now you can see more movement of the needle. In fact, if I go very slowly, you see just a little bit of a deflection. And if I go quickly, you see a greater amount of deflection. Also, as the magnet is going in, the needle deflects to the right. And as I pull the magnet out, it deflects to the left. But when the magnet isn't moving, there's no deflection, indicating no current flowing. Okay, so when the magnetic field is changing going into the coil, there's a positive current flowing. When it's changing coming out of the coil, there's a negative current flowing. And now let me connect the 100 loop coil. And I'll start by moving the magnet in very slowly. You see a deflection to the right, pull it out to the left. And if I go in quickly, you see a much greater deflection. Okay, so the rate of change of the magnetic field affects the current also. We saw that as the number of turns in the coil increased, the current increased. So the current is proportional to the number of turns, which we'll use N to represent. We also saw that the current increased as the rate of change of magnetic flux inside the coil increased. So d psi dt represents the change in the magnetic flux inside the coil. Now, if we were to monitor the resistance of the whole circuit, that is of the coil and the wires and the ammeter, we would find that the current was inversely proportional to the total resistance of the circuit. Now, this equation is usually written as I is equal to minus N over R d psi dt, and we'll talk about the significance of this minus sign in a future video on Lenz's law. So now if we multiply both sides of the equation by R, we get Ri equals minus N d psi dt, and resistance times a current is a voltage or a potential. We call that the electromotive force. And so the electromotive force is equal to minus N d psi dt, and this is known as Faraday's law. Here's an illustration of the way Michael Faraday actually performed the experiment. He had a coil of wire that he attached to a battery, so the current flowing through this coil generated a magnetic field. So that was the magnet he used, was an electromagnet. He had a coil with a larger diameter that was attached to an ammeter. So then by moving the electromagnet in and out of the larger coil, he could detect the induced current on his ammeter.